Yeah, so I will pass the floor to Olga. This is the, let's say, the second online technical workshop that we have prepared. We make once last week related with the steel and aluminum industry, and today is with the cement industry. Okay, that's also the first one was presented by Olga. So Olga is working in IBL, in the Swedish Environmental Research Institute, and she's working in the energy system modeling, the life cycle costing, climate change mitigation, etc. So yeah, they are leading one of the tasks of the RETROFEED project. So Olga, the floor is yours.
Thank you, Diego. Yeah, could you maybe start sharing our presentation, because don't have access.
Okay, I'm going to share. Yeah, I thought I was sharing the screen. Yeah, sorry.
Hello everyone, and welcome to our second online technical workshop towards more efficient cement industries. Thank you for participating this event. Our agenda for today was designed to ensure a productive experience for all participants. And with the workshop, you will have the opportunity to learn more about digital twin in cement industry, flame visualization monitoring tool, quality measurement monitoring system for clinker, main achievements on cement demo sites. Also, we will be happy to answer all your questions. And now we would like to present our project and give you a short introduction of the RETROFEED project. So Roberto, the floor is yours.
Hello, good morning, everyone. My name is Roberto Arevalo, and I coordinate the technical activities in RETROFEED. So I'm just going to give a brief overview of the whole project, and then we pass to the technical activities. So the whole title of the project is the one you can see on your screen: enable the use of increasingly variable, bio-based, and circular feedstock in process industries through the retrofitting of core equipment. So this is mostly a circular economy-based project in which we aim to use more feedstock in general, which be different in each industry that was before considered a reject, and now we can use it to improve the energy efficiency, to reduce GHG emissions, and in general to improve the functioning of our industries, in particular in the sector of energy-intensive industries, which are very different among them. We have industries in the ceramic sector, cement, aluminum, steel, and agrochemical. In this slide, we can see a pictorial representation of the whole project. At your left, in the picture, you can see in the center the core equipment, which is going to be retrofitted in each industry. In each case, it is going to be something different. It can be a furnace or a chemical reactor. Each one of them is going to be retrofitted to allow the use of some feedstock that was before considered a reject and now can be valorated as a fuel, for example. And also these core equipments are going to be modeled in each case by a digital twin. Upwards and downwards, this core equipment, we find other processes that will be different in each industry, and they are also going to be modeled using different modeling technologies, including machine learning. And all these models are going to be included in what you see below, the DSS tool, the decision support system, that apart from the models for the core equipment and the other processes, it also includes the definition of key indicators. It allows tools to calculate CapEx, to schedule production, to forecast prices of energy and other feedstock. So it is a complete tool to manage decision support at several levels, at the level of the, for example, of the operator of core equipment, of a manager scheduling production. On top of this, we are also improving the monitoring and control system in each industry, including novel monitoring systems like image systems, for example. And we are connecting this monitoring with the DSS, so we have real-time information of the processes. Finally, our solutions aim at a relatively high level of TRL, which is 7 in all cases. Next, please, Diego. So we are now going to be a brief overview of the goals in each industry. In CETIL, which is the cement sector, we are aiming at reducing CO2 emissions, replacement of fossil fuel using RDF, which will increment energy efficiency. And we are also improving the monitoring using novel systems, like, for example, the cameras. In this industry, we are currently doing all the retrofitting, and in the next weeks, we will start to obtain the results. Next one, please. In ASAS, in the aluminum industry, here the retrofitting has already been completed, and we already have the preliminary results, and we're happy to say that the goals have been fulfilled in all the respects that you see in your right. We have increased the amount of scrap that is used. We have reduced the energy consumed, and we have also reduced the GHG emissions. In the next one, in the steel sector, the retrofitting has been completed in the 2 demos that we have, and we are now doing a test with alternative sources of carbon, which is biochar, and well, they are promising so far. In the next one, in Torrecid, in the ceramic sector, here we have already completed the retrofitting and the models. And again, like in the case of aluminum, we are happy to say that we are achieving our goals. There has been a reduction of energy use, a reduction of fuel consumption, and in turn, we are reducing the GHG emissions. And finally, in the agrochemical sector, in Fertiberia, well, here the retrofitting is not yet completed. It will be completed in the next months, but we have completed all the models, the simulations, and we have run some scenarios that indicate that the results will be very good. And finally, the goals, an overview of the goals that we are attaining that are, we think that are ambitious, as should be, but we are happy to say that in the preliminary results that we already have from some industries, we are reaching these objectives, so we can see that our project is resulting successful so far. Thank you.
Thank you, Roberto, very much for the project presentation. And now we will talk about digital twin in cement industry. So Antonio, please.
Thank you very much, Olga, and thank you all of you for attending to this workshop. I am Antonio Alcaide. I am in charge of the technical development of the digital twin for the cement industry, and also in charge of the work package for the validation of the solutions implemented in this project. In the following 10 to 15 minutes, I will show you a brief description of the digital twin development process. And well, let's start. Diego, can you pass the next slide? Thanks. This is a brief index of what we are covering. We will talk a bit about the context and the problem definition of this digital twin model. After that, the approach on all the challenges that arise when we were developing them. We will talk a bit about the model development, and after that, the results from the validation and the fine-tuning of this model. And after that, some brief conclusions to see how the development was in an overall view. Next slide, please. Okay. Regarding the context and the problem definition, we can see that the main problem with the cement industry is that it is a very energy intensive industry, and it accounts for let's say 5 to 8% of the global CO2 emissions from the past decade. It is a highly energy intensive industry with 3 to 5 gigajoules per ton of clinker in energy demands, and the fuels usually account for 30 to 40% of the cement production cost. Therefore, there is a need to develop new solutions to face these challenges. The alternative fuels are a very good way for accomplishing these goals, as my fellow Roberto told in the previous slides. Alternative fuels allow the reduction of fossil fuels consumption, are cheaper, and also a good solution for avoiding the landfilling of wastes. From these alternative fuels, the ones that were used in this demo site are the refuse-derived fuels and also tires. The alternative fuels can be from very different origins. They can be waste oil, used tires, plastic solvents, also bio-based, agricultural waste, wastewater sludge, rice husks. But the refuse-derived fuel is available from the municipal landfilling and mostly contains plastics, paper, cardboard, textiles, and also fluff. Coming from municipal solid waste, this is a low quality fuel in terms of when compared with the classical fossil fuels ones. It has high moisture, high ashes content, a big size, a large heterogeneity. The moisture can range from lower than 10% to as high as 40%. Ash can be as low as 4 to a quarter part of all the content of the combustible. Low heating value can vary between 13 up to 30 megajoules per kilogram, and the size can be ranged from very little particles from 1 to 150 millimeters even. There is therefore a complex combustion behavior given the heterogeneous nature of this fuel, and there is a very high heterogeneous mixture of solid particles. They are non-spherical. They have different thermochemical properties, combustion kinetics, and also the flight behavior of these solid particles is very different given the heterogeneity of it. Here you can see a picture of, let's say, typical sample of RDF taken just from the tanks in the Cecil demo case, and you can see the heterogeneity I mentioned before. Next slide, please. Okay, regarding all the manufacturing chain of the cement industry, we can say that the main energy-intensive process is the fourth one, the clinkering one, in which the raw material falls down the cyclone tower, enters the rotary kiln, and there is a thermal chemical process in which the raw material is converted into the clinker pieces that are the main components of the cement. That is the process we were focusing on, for which we have developed the digital twin model. Next slide, please. Okay, given the clinker production requirements, the very complex physics inside the kiln and the low quality of the RDF, there is a need of performing a specific and ad hoc digital model, in this case, to assess the effects of the relevant variables, provide support to the operators when they are increasing the RDF shares, and testing the what-if scenarios when changing several different parameters for the operation of the rotary kiln. For that purpose, we made a computational fluid dynamics model of the rotary kiln in order to solve the combustion of the fuels. Remember that we are introducing a share of petroleum coke and the refuse-derived fuels, both at the same time from the burner, and they are intended to burn all along the length of the kiln. So the CFD model purpose is to capture how this happens. After that, we needed to develop a simpler model in which we can test different operational parameters, ranging from the different inlet temperatures, different charges of raw material, different amounts of fuels, different amounts of combustion air. For that purpose, we did a 1D slice model in which we solve clinker and gas temperatures and composition by solving energy, species, and mass balances all along the length of the kiln. Next slide, please. Okay, the challenges for these developments were different. Here is a brief description of the main of them. Given the one-dimensional nature of the final digital twin model, the local peak values for the temperature are not computed. Also, the local sinks of oxygen are also not computed. These make a problem to arise, which is the minor pollutants formation, which cannot be considered. Therefore, our 1D model does not provide this information to the final user. Nevertheless, the oxygen availability for the fuel can be computed by using the CFD simulations using representative fuse mixture. We capture the burning of the particles and compute the local sinks of oxygen. Then we introduce this information into the one-dimensional model. Also, the flight of the particles cannot be captured by a one-dimensional model, but the CFD simulations can provide us insights of this behavior, and then we can add this information to the one-dimensional model. Another challenge is that the radiation thermal transfer is difficult to be captured by this one-dimensional model, and it is computationally expensive. Therefore, for this version of the model, we have not developed these radiation flux, but we used rough estimations, and after that, we did the fine-tuning of the model to try to fit to the validation points. Next slide, please. Here we can see an overview of the two developed models. On the left-hand side, we can see an example of the temperature profile capture with the CFD model. We can see from the left side that there is the entrance of the combustion air and the combustion solid particles, and we can see that very detached from this burner side, there is the actual combustion and the burning of the particles. This very detached flame is due to the low quality of the refuse-derived fuel, which has to be very well mixed with all the air and all the pet coke to start burning. Therefore, we find detached flame and also moved peak temperatures compared with the typical combustion of fossil fuels profiles that we can find in older kilns. On the right side, we can see the discretization of the model for the one-dimensional model. Can you please, Diego, click one more? We can see. Yes. Here, what we have done is to split into different slices of the model, or the kiln, sorry, and we solve the gas phase from left to right side towards the cyclone towers model. We solve the cyclone tower to relate the inputs at the top of the tower to the outputs at the outlet of the tower, and then we solve in the opposite side the clinker phase, and also solve the interaction between them in an iterative process. Next slide, please. Okay, here are some results from the validation and the fine-tuning we have developed. These are results from the CFD simulations we performed. We did a set of 6 simulations with 3 different RDF, let's say, statistically representative mixtures, and also with 2 different RXS from the secondary air that is entering into the kiln. On the right side, we can see the percentage of each of the introduced fuels, petcoke and RDF, that are converted into volatiles, fixed carbon, and moisture released to the gas phase all along the burner. These profiles are later introduced into the one-dimensional model and added to the energy balances, species balances, and mass balances. What we can see from the simulations is that the increased moisture we have in the RDF, the, let's say, more detached flame we obtain. This is, let's say, a very straightforward result. The higher moisture content, the higher energy is needed to evaporate it, so later the combustion starts. When we increase the excess air, we can see that the RDF burnout fraction also increases. But this is not very linear, and we have found that increasing the excess air does not have very high effect. Let's say that the RDF burnout fraction within the ranges we have tried keeps more or less stable. Next slide, please. Okay, these are some examples of the results we can obtain from the one-dimensional model. This is important to note that we have 14 empirical parameters that cannot be estimated nor measured in the kiln, and we had to estimate them adjusting to a set of validation points to make this model fit to the ad hoc cement rotary kiln we have in this demo site. We obtained 6 validation points. We used a meta-heuristic method, and we obtained a set of the parameters that fit well with the experimental results. On the left side, we can see a comparison between the first digital twin version, in which these empirical parameters were not very well optimized. And in the right side, we can see the second version of this digital twin with an increase in the accuracy of the results we obtain. We can see from the right to the left side, the conversion of the raw materials composition to the clinker composition. What we have done to validate this is obtain the last point of these curves, the one at the left side, and compare it with experimental results from the demo site. What we can see is that thanks to this meta-heuristic method optimization, we have an increase in the accuracy by doubling the accuracy. From the first version, we had an overall weighted error of 10% between the composition we computed in the model and the real one. And now we are having, in this enhanced version, a 5% of error, which is a very good result. We are also facing some uncertainties regarding the input of the secondary air. We expect this to be measured in the following months and increase a bit the accuracy of the model. And next slide, please. Here we have some conclusions of all this work carried out during the digital twin development. We characterized all the fuels, petcoke and RDF, by using historical data and taking into account the variability in time. Also, we did some granulometry analysis and size distribution measurements in an in-house test carried out in our CSF facilities. We can say that the RDF is a very heterogeneous mixture of fuels, and this needed to be simplified to introduce into the numerical models by these statistically representative mixtures. And we have seen that the CFD model is a very powerful tool because it captures the complex behavior of the RDF particles, flat and burning, and provides accurate information to the one-dimensional model. Furthermore, we can see that the general flight and the burning trajectories of all the 3 different RDF mixtures is more or less similar, which is a very good result, which helps to reduce some uncertainties when changing the RDF supply. Well, we can see that the modeling approach considered here, which is a hybrid between CFD and 1D, seems to provide realistic output estimations in a qualitative way and avoids very high computation times for the decision support system and to the operators working every day. And well, that's everything from my side. Thank you very much for your attention.
Thank you very much, Antonio, for so detailed presentation. Yeah, and the next topic we discuss in this workshop will be the flame visualization monitoring tool. So, Giorgio, please, floor is yours.
Okay, thank you, Olga. Good morning, everybody. I am Jorge Arroyo. I work in the digital industry team, TIRCE. I'm gonna give you a brief introduction about the flame visualization developed during the RETROFEED project. Please, next slide. First, an introduction to the combustion monitors in energy-intensive industries. An usual scheme is in the left of the slide, as you can see here. Whether to develop a monitoring combustion diagnosis system, you need a combustion system where fuel air, when some of the variables are important, like the temperature of the pollutants. Some of the process variables are measured. Depending on the industry, we have found that a lot of variables are measured or just a few. And we often, in these furnaces, we can have access to the images of the flame or the flames, even if we are talking about several burners. And the idea is to develop predictive models to diagnose or to make some alarms about the malfunctioning of the system, or even to predict some variables like the equivalence ratio, the combustion, or similar. In the right, you have some examples. We have worked in the last year for the steel sector. It's important to mention that it's not for a diagnosis system based on images. It is not need that the image in the visual. We can work with the ultraviolet, like in the case in the chemical sector. And you can see here also an important part of the development is the laboratory, where all the variables are measured, and it allows us to start the trainings and to test some algorithms, because it provides some information previous to the industrial developments. Next slide, please. All developments we have been working on were based on gaseous fuels. We recorded the images, and with post-process, let's say the innovation in the RETROFEED project was first we were going to work with solid fuels. In the case of Cetil, you can see here, and it's the rotary kiln that Antonio explained in the last presentation, where you have a camera installed in the base of the burner, and you have images like the one of the left, when you expect to see the burner, the flame, and the clinker. But the reality is that we have the images of the right, when there are some overexposing frames, where you can find some dust coming from the air. So there are no perfects. Next slide, please. So in the RETROFEED project, one of the first decisions we took was if we could use the video system, which was installed in Cetil. We know that it's an analog video system, but there are some benefits, like that no additional installation was needed, low investments, since we didn't need another camera. It was easy to replicate, because if we worked with installed cameras, there are a lot of combustion systems with cameras, and we can't apply and develop our algorithms with the images coming from those cameras. And that the current camera has the best location of the furnace. If we install a new video system, the point of view was not going to be the optimal. On the other hand, the video conversion was difficult, and one important point was that the camera parameters were fixed. So we couldn't change important parameters for video processing, like the exposure time, brightness, etc. So we recorded some videos, and we realized that the processing was feasible with the current video system. But on the other hand, we had low quality videos, and we knew that we were going to need a lot of videos to train the algorithm successfully. But the idea of the project is to use a current installed video system. Next slide, please. So we started the development in 2 ways. One, as I mentioned, in the laboratory is important, and another, the industrial. In the laboratory trials and the retrofit, we tested the artificial intelligence algorithms under control conditions. In this case, what our first objective was to train the acquisition system for real time. For us, this was just an innovation because, as I mentioned, we work always over previously recorded videos. So we use a setup in order to extract images and try to process in real time. On the other hand, we work with frame pictures, and we applied some trainings models, and we wanted to start to define the processes of labeling pictures, of test some neural networks, and test and validate. Next slide, please. In parallel, we mounted a setup in Cecil, in the plant of Cecil, where we used a video converter to convert the analog video system of the current video system installed. And we made a bypass in order to not interfere with the normal operations of Cecil. And we work with remotely with a computer. As I mentioned, we could connect from Zaragoza to Cecil wherever we wanted. We define a video campaign to record videos for the training, and Cecil provides us also all the process data. So we have a good start for start the training of the real images. Please, next slide. Since we had a lot of videos and of data to label, etc., we applied clustering first using the K-means algorithm to deselect the videos and conditions suitable for training and processing. And we made the clustering based on some parameters of the process, but we realized that the cluster was working better using the 2 parameters, which was the alternative fuels flow and the fossil fuel flow. So we separated in some groups. You can see here, for one example, in the left, and we started the training of the algorithms with the videos. Please, next slide. This slide summarizes the training, the process of training. So the input was the images of the video campaigns. We have worked with some models in the laboratory and in the real industrial process, some models for segmentation and some neural networks. We use the your algorithms. If you work with artificial vision application, you will know, because it's used to identify elements in videos and images. And finally, we develop an app with an output that in the next slide, please, Diego. Actually, this is a video. Diego, can you play it? The final flame monitoring application has a graphical interface where we segment 3 elements of the flame. You can see here the clinker, the plume of the flame. We identify these elements, and we characterize the area of each element. You can see here and some geometrical features. In this case, the percentage of the image is the amount of the size, the amount of pixels of each segmented part compared with the whole number of pixels. But we are working also in extract some other statistical features of the image. and texture features. As I mentioned, one innovation of the application is that it can work in real time with a actually with a good frame rate. And in the next slide, at this moment of the project, which is finishing, we are working on adjusting some models and extracting more features, but I wanted to show here some developments for the future. One is we will need to validate it under real condition for long periods of time. To this, we will need the feedback from operators. In this case, we don't connect to the process data in real time. This was not in the scope of the project, but also we recorded all the features of the image, and one work to carry out after the project is try to match these features of the image with real process variables, and in a further step try to make it on real time. And of course, one important thing is try to replicate this in other plants, the cement plants, and in other sectors with rotary kiln, like the mineral or so on. And that's all from my side. Thank you, everybody, for your attention.
Thank you, Giorgio, for the presentation.
You are mute, Olga, actually.
Thank you, Giorgio, for the presentation, and hope you will successfully finalize all these goals that you presented last time. So the next presentation is quality measurement monitoring system for clinker. And Francisco, the floor is yours.
Yes, good morning. Yes, okay, so this deals about how monitor the quality of clinker. So next slide, please. Yes, so the objectives of was to monitor temperature and size of a clinker and estimate some phase, CCN phase, free line, C2S, C3S, but allow to determine quality of different clinkers that are coming out in the flow from coolers. And here the principles, the main challenges are to deal with a harsh environment. And I will explain why it's a very harsh environment, factory integration factors, and how to deal with that, and how can we make a modular system and make some integration and optimize all the system that has been developed for integration. And I will talk about and give some ideas about system architecture and data analysis. So next slides, please. Yes, this is right now the general architecture that has been proposed for the temperature and size measurements that is done in two different locations in the factory. One is in the transportation belt and is monitoring directly temperature and size coming from flow, production flow. And the other one is will be located in this case in the conveyor pipe that is doing a sampling of production to be analyzed with XRD and XRF system. So as you can see, the two systems, are each one of the system are composed about two different electrical cabinets with communication system. Here we have to deal with some long distances. So for more than 100 meters, for example, from system that is installed in the transportation belt. And the system that is installed in transportation belt is composed by a profilometer and a thermal camera. And the system that will be installed in conveyor pipe is composed by the Swir camera. So I will explain, give more some details about what kind of technology has been selected. So next slide, please. Yes, here, when I say harsh environment, one of the main enemy for optical and vision system is the dust. So here we have to develop a system that will maintain, assure, and will protect all the optical and vision system from dust, and will keep maintain functionalities, degrees of freedom, and allow also to make some good positioning and focusing of all the systems, and at the same time be a very robust system. So here we have selected for a thermal camera ERS6 from automation technology that has a very good accuracy on thermal range. It's a long wave infrared system. And for profilometer, we have selected a system for also from the same manufacturer, from automation technology. Each of the system internally are protected, and they are granted in protection grade 65 and 67. But as I have explained, dust is a very complex problem for optics, and we have developed a specific protective system with some curtain here in order to protect the windows and avoid some dust depositions. So next slide, please. Thank you. So here's the system integrated in transportation belt, and you can see there is two different cabinets, as I explained before. A small one that is in charge of allowing a regulation in power supply and communication, but is fitted with some optical fiber routers. And the other one that is the most main cabinet that will contain, will enclose all the processing units for this system. This, of course, will be connected to a central computer in order to collect all the data. So the next slide, you will see some of the results. So if you can click 2 times, please, for yes, and the second one. If you could click also, yes, thank you. So you can see 2 images, some results. On the top, you can see the thermal images that has been captured from the camera, and we can extract an histogram from obtaining, getting some temperature distributions. And below, you can, on the bottom, you can see the laser line that is projected directly on the clinker floor, and then we can get some very precise images, and we are now processing with PCL and Python libraries in order to extract the size of clinker. So we can get some very good quality for estimation of the size. And when we have this system has to be optimized, improved. I hope to do this by the end of September in order to really get some better results and estimate in real time temperature of a clinker flow, detect some hotspots, and allow also to have an estimation of the size of and maybe volume of a production. So in the next slide, yes, this is a system that will be integrated for measuring temperature and size in the conveyor pipe. It's a quite different system from the other one because it integrates a camera that is working in a short-wave infrared range. And this system is composed by a PC panel with an electrical cabinet in which there is a PLC system that is controlling the opening and of a window, door, and air curtains in order to protect all the enclosure from dust projection. This system is also could be triggered automatically from factory. So in the next slide, you can see the enclosure that has been developed in assembly in IMAN. So electrical cabinet, and you can see in the bottom one of the aspects that is important is glass selection. It's a Boroflat glass that allows more than 90% transmission in the shortwave infrared range. So in the next slide. Yes, this is how we have dealt with the fact to reduce technical visit to the factory and optimize the development. We have developed in Neyman a specific test bench with a conveyor pipe system that simulates with a pneumatic system the movement of a clinker flow inside the pipe. We have made some tests with 2 different cameras. We'll show you some results. But here you can see in the video how the clinker is moving, and this, I think, quite similar to what we can expect in the factory. So in the next slide, yes, in the next slide, you can see some results what we have obtained with this test bench. On the left side, we have tested 2 different technologies of infrared camera. One working in the long wave infrared range, that is the images that you have on the left, is based on silicon microbolometer technology, and is working in 8 to 14 microns. And the second one is a 301 that is working from 900 to 1,700 nanometers in the shortwave infrared range. So there are 2 different kind of images. To give you an idea, right now what we have concluded is that for this kind of material, for clinker, it seems that a low camera is working much better when temperature is below 160 degrees. So in the bottom of this slide, you can see some examples of segmentation that we are doing for each kind of detection of capture of images on the 3 images. You can see that we can, with different processes, binarization and detection, some typical step for segmentation. We can make some detection and estimate and detect the smallest and the biggest clinker. We can also extract, and we are extracting also some histogram distribution of different size in order to have a complementary information. So now in the next slide. Yes, I will talk about some more, I would say, tricky part of the project, that is the phase estimation. Right now, the reference system is based on XRD and XRF technology that allow you to have a very precise measurements of content of different phases. Here in Neyman, we have tested different systems, and we come to the conclusion that based on infrared technology, the most adapted would be to do some spectrometry measurements. So here you can see on the top of the slide that there is a different wavelength that are characteristic of different phases, in this case C3S, C2S, and Portlandite. And in the bottom, you can see the spectra we have obtained with different kind of samples. And what is very important here to point out is that the state of and the format of the different samples has an influence on the distribution and the dispersion of a measurement. And the best quality, I think, is obtained for grinded materials or compacted materials. But in this case, we have to take into account that there is some interferences coming from resin that is used for compacting the samples. So now this result has to be correlated with XRD and XRF system in order to establish some empirical law that could allow to estimate Portlandite, halite, and baelite contents. So in the next slide, you can see the last proposal that we have done from Neyman to Cecile. We have also worked on another system that could be installed directly on the conveyor pipe to make an extraction of raw material, but taking into account delay and time that we have in the project, I think that it's more reasonable to go for a lab test first. And we have developed, we are also worked on spectrophotometry. This is a common path spectrometer developed by Arco Optics. And we are worked together to develop a specific tool for capturing, for making the acquisition of spectra. So you can see some details of the internal structure of this customized tool, in which a specific developed mirror is focusing on the tablet samples. And the detection right here of the system that we have proposed is done by a photoelectric sensor. So this photoelectric sensor will detect, and we have tested right here in AMEN. It is working quite well. It's detecting when some new tablets is arriving just above the spectrometry system and launch the acquisition. So this system should be integrated in the next week in Cecile, and we are right now manufacturing the mechanical system. So to conclude, in the next slide, I would say that we are still a lot of work to do, but well, we have some, I would say, very interesting result from temperature and size measurement system. One is integrated already in transportation belt, and the other to be integrated in the conveyor pipe. And we have some tuning works to do and some deep analysis to correlate spectrometry results with XRD1. But I think this could be done, and well, it's something that is already established in bibliography and could provide some interesting results. So for my side, it's all, and I will let the floor to the next presentation. Thank you. Yes.
Okay. Yes. Thanks, Francisco, for the presentation. So yeah, I don't know if.
Okay.
Yeah, Olga is having some troubles.
It's okay. Yeah, you can hear me. Yeah.
Yeah, perfectly. We have seen the heard you pretty well during the presentation. So yeah. So I don't know if Olga have some problems. Okay, so in any case, thanks, Francisco, for the presentation. So let's move to, let's say, the last presentation of today. That will be done by Walter. So Walter, thanks for being there. So the floor is yours. You can explain your presentation.
Thank you, Diego. Good morning. I'm Walter Tovar from Cecil, a Portuguese company, a cement company that represents the cement industry in RETROFEED. Next slide, please. Okay, so this project is perfectly aligned with the cement industry's greatest challenge for the coming years, reduce the carbon footprint of cement production. So we proposed two major challenges to improve our environmental performance by replacing fossil fuels for alternative fuels, reducing the CO2 emissions, and to increase the knowledge about the cement production process, because we are aware that we still do not control all the important process parameters, and we need data to achieve optimization. This means production the same quality cement with less raw materials, less energy, and less environmental impact. Next slide, please. But why working in alternative fuels? Fuel emissions account for around 35% to 40% of total CO2 emissions from cement manufacturing. This means that a small reduction in fossil fuel share has a big impact in CO2 emissions. The alternative fuels come from waste or byproducts and can be biomass, fossil, or mixed alternative fuels. Cecil uses mainly RDF, originating from municipal solid waste, whose alternative disposal option is incineration or landfilling. So it's important to understand that CO2 is saved by replacing fossil fuels with the alternative waste streams in the cement plant, but also through those emissions not being made by incineration or by methane emissions from landfill. So this co-processing is very important for the circular economy and plays a key role in terms of waste management. The extremely high temperatures and residence times reached in cement kilns also ensures that these wastes are managed in a safe way. Next slide, please. The RDF has advantage, but comparing it with the traditional fossil fuel, the petroleum coke, we easily see the challenge associated with this replacement. We are replacing an homogeneous fuel in powder form with a high calorific value by a very heterogeneous fuel with a lower calorific value and high humidity. This poor quality fuel will cause instability in the production process and quality problems in the clinker. This was the challenge presented to our project partners. What changes should we make to be able to use more RDF? Next slide, please. The kiln models and the trials made in the burner prototype showed that the increase of RDF share above 60% can have negative effects on the combustion behavior by increasing the ignition time, extension of the flame length, and decreasing of the overall temperature in the kiln. But no significant modifications to the kiln main burner are necessary to reach high shares of RDF, but it was recommended to split the RDF flow into different streams, allowing a better mixing of the fuel with air. It may be possible to combust up to 90% of RDF by using an additional reactive fuel like hydrogen. The use of hydrogen in the kiln burner increases the RDF ignition, brings the flame closer to the burner, stabilizes the combustion, increases the temperature peak inside the kiln, and reduces the CO2 emissions. Considering all these conclusions, we decided to install a secondary burner above the main burner and to use a nitrogen injector inside the main burner, like you can see in these pictures. Next slide, please. The kiln models also confirmed that we need to measure new parameters to control our process. So, in addition to the new clinker sensors and the flame tool, we installed also a new gas analyzer in the kiln inlet to control the kiln combustion, a new sensor to measure the RDF calorific value and know the total energy that we put into the burner, 2 acoustic flow meters to measure the gas flow from combustion and the combustion air flow, and an acoustic thermometer for the secondary air temperature to know the clinker cooler efficiency. Next slide, please. After all these modifications, we are ready for the next stage, testing and validating results. Tomorrow, we start the retrofit tests, and although the project ends in October, at CESIL we feel that we are just starting because there is much to be done in terms of burner and sensor tuning, process optimization, new control strategies, development of predictors, and also the hydrogen trials. So that you can understand the importance of RETROFEED, I remind you that the European Cement Association, the CEMPURO, targets to reach 60% alternative fuels containing 30% biomass in 2030 and 19% alternative fuels with 50% biomass by 2050. And RETROFEED shows that we can achieve this target in the next years by using green hydrogen. Thanks. That's all from my side. And please let us know if you have any question. Thank you.
Thank you, Walter, for sharing your insights in this project. And now it's time for questions for our speakers. So,
Yes. So I don't know if someone have any question or any doubt from the audience, or you can write in the chat, or you can raise your hand, and we will pass you the floor in order to ask to the speakers. If not, well, maybe I can start with some question, and then if there are anyone that are interested in have more information about any speaker, he or she can ask. So yeah, let's start with you, Walter. So yeah, I know that you are now integrating of the solutions. You have installed or you have commissioning the satellite burner last week. Yeah, in order to use more RDF in your factory. So I have a question related with yeah, I don't know if there are some legal barriers to use this RDF or something like in Portugal in that case, because I know that in some other countries from Europe, for example, here in Spain, there are some restriction to use the solid urban waste as energy, let's say. So I don't know if in Portugal you have any problem, or you have to, or in the past you have meet with some of the governments of the regional or the national governments to allow the use of this solid urban waste in your factory.
Thank you, Diego. Yes, we have some legal constructions. Each plant has environmental permit that indicates all the types of RDFs that we can receive in our plants. Okay, so each code of waste is listed in our environmental permit, and also the amount of each waste that we can burn. Okay, so okay. And each modification needs another environmental permit. Okay, so we always have to change the environmental permit if we need to add some new waste.
Okay. So it means that, for example, now you are testing this solution in one burner of the plant. If finally you decide to make also this modification in the second one, and use more RDF, so probably you have to modify your plan or your emission.
For sure. And even to use the hydrogen, we also need to modify our permit.
Okay, yeah, because some of the things that you have also indicated that you have to use hydrogen, and in the future you want to use more hydrogen in your plant. So you have talked about the green hydrogen, but I don't know if you think that you are able to use this kind of green hydrogen in the close future, or you need more time to, I don't know, to produce your own green hydrogen, or maybe to purchase this green hydrogen from some from some places from Portugal. So I don't know, which is your opinions from this?
Yeah, the green hydrogen is not available at the moment, but we are in other projects where we intend to have the green hydrogen available in next years in the Maceira plant. Okay, there's a project to produce green hydrogen near the plant and to feed several industries in that area.
Okay, yeah, I think that that's the point. So I know that also from other points of Europe and also in Spain, that for example in Fertiberia, that is another partner of RETROFEED, they are having other projects in order to produce green hydrogen very close in order to use in the factory. So probably this is one of the future, okay, of the green hydrogen, to produce and from the same factories and to using it, because if not, well, the cost could be very high. But okay, so yeah, that's,
I think at least at the south of Europe, it's possible to have this green hydrogen. Okay, because we still have sun, but I think I know that we also, I think Fertiberia also has other projects in the north of Europe to produce hydrogen, green hydrogen with the wind.
Yeah, I don't know if Fertiberia, but we know about some also other projects that are using wind instead of sun, like in the southern Europe.
And the great advantage of hydrogen is CO2 free. Okay, and like the models shows, we still need high quality fuel in our burner, and hydrogen seems the best solution at this point.
Okay, so
Okay.
let's see in the future, but at least you have the first step for that. So thanks, Walter, for the clarification and for the presentation of the things that you are doing in Setil. So interesting.
Thank you.
Perfect. So I have also some questions for the panelists. So probably, yeah, we can continue if there are no ones that want to ask something. So for example, for Antonio, well, after the presentation of the digital twin that you have made for the cement sector, so as you have explained, you made first the first version of the digital twin. You have made a second version after the improvements, and theoretically now you are going to make or try to make the third version after the validation phase, or with the results that Setil is going to obtain after the implementation of the solution. So which is your feelings? Which parameters do you think that could be more critical, or maybe they can change or not, or probably they make more the same value? So I don't know. What do you think? What will be the more critical aspects for this validation phase?
Hi, Diego. Thank you for your question. It is difficult to answer to that question because several parameters can affect the work of the kiln, but the most important one is the availability of the secondary air mass flow, and also if the temperature changes pretty much. And we are very confident in that the whole process will not change pretty much. But if there is a very high increase, for example, in the RDF share, we may need to fine-tune some of the parameters for the digital twin. We are confident that with that fine-tuning, we can provide good insights into the response of the burner, of the kiln, sorry, because it is based on energy balances. But we are not expecting several problems in this sense, because as we know, the only change will be to try to increase a bit the RDF share. Let's see what happens and try to fine-tune these parameters. But if the secondary air would suffer changes, that would be challenging for us. But we are not expecting to have those problems within this final phase of the project. Yes.
Okay, perfect. So finger crossed to avoid any challenge or any big challenge, just to adapt a bit the results of the digital twin and the fine tuning. So okay, perfect. Thanks, Antonio. So I have also a question for Jorge about the flame monitoring tool that you have developed in Cecil. In that case, you have indicated during the presentation that you have you have used an analog system, the analog camera that Cecil has in their facilities right now, instead to change to another one. So I don't know if for you, after see all the results and you see all the things that you have done, so if we back 3 years ago and we started making the development, you will make the same using the analog system, or you indicate okay, we have to change the system and try to make or use a digital one. So just to know if you think that the results will be great, or the process to obtain the models has been enough with this analog system, or not. Do you think, okay, maybe if we came back 3 years ago and we'll say, great, we have a lot of money, we change the camera and use a visual one and try to make the models from another point of view, let's say.
It has been challenging to try to develop some algorithms that you are used to see in computer vision application. You can
see good images, all is clear, the detection, the cameras have high resolution. But I think that for this project, it was a good decision to use this, because we are in an innovation project. We are in the worst scenario that we have an old system with low quality images, so it's challenging to get results from this. But we have obtained some results, so I think that it favors the replication of the tool, let's say, because what we have found is that a lot of industries have some cameras, and if we can connect that images and make some algorithms, it's cheaper and easier because you don't interfere in normal operation. And in this case, even though we have some budget to install another camera, I think that it was a good decision. It was so we installed our computer, our bypass, and we could connect thanks to Cecil for giving the connection whenever we wanted, record videos at any moment. So we have all. But on the other hand, what we would have liked to change some image parameters that in this case they were fixed, because the operators work with some very fixed images, and they have the knowledge and they have the experience to look into the monitor. And for us, this was a very, very important drawback. But in this case, I think that in a scale, it with the current solution.
Okay, perfect. So yeah, I understand that it's a challenge, but of course, if you have been able to use the current camera, has been good for you for learning more things maybe about these images, also for Cecil, that they don't have to change.
It is easier to reach other industries, saying that we just need to connect to your video. That no, you need to modify your furnace, your kiln, install a camera. You need to spend a lot of money in a first step. So for us, thinking on the future and in the replication in other industries, it's really easier than installing a new system to work with the current.
Perfect. Yeah. I think that this point of the value of replication, it's great, not only for the project or for Cecil in the case if in the future they want to replicate or the solution, also for the European Commission. As you know, one of the most important things for the European Commission is that we develop some solutions that could be very easy to replicate in other sectors or in the same sector, in the same factory. So that's very, very good results. So thanks, Jorge, for the explanation.
You're welcome.
If there are no more questions from the audience, no, so probably I can make the last one related with in that case to Francisco and the development that they have done in Cecil. So Francisco, I don't know if you are able to.
Yeah.
Okay. Yeah. Perfect. So
yes, I will switch the camera.
Yeah, great. So we have seen the lot of the developments that you have made with a lot of challenges, because we didn't remember the COVID-19, but we have a lot of restriction to visit the Cecil, to make some travels to visit Cecil, to visit the plant and try to make some more developments, and you have made some changes and some modification until, let's say, last minute, like the laboratory developments, so the spectrophotometer that you are developing in the laboratory. So just to my question is related with the with if you can explain better the advantages or the advantages of this solution for Cecil and for not only for the plant, because I don't understand, but for the other plants, if you are going to make the replication in other plants of Cecil or even in other industries. So you can explain a bit more the advantages of this solution that finally you have decided to perform.
Which one of the solution? Temperature,
Yeah,
size, measurement,
yeah,
or spectrophotometer, or the whole one?
Yeah, the whole one, but the one that you have developed for, or the last decision about the one that you are going to install in the laboratory with the transporter line and something. Yeah.
Okay, I will start with this. Well, what should be clear is that with spectrophotometry solution, what we intend to do is not to make a precise determination of the phase, the chemical phases, because the reference system that is used right now is the diffractometry system, is the best one. This is clear, and this is stated for a long time right now in the industry, in cement industry. But the great advantages, I think, using a spectrophotometer could be to have a very reduced system, compact system, for a cost that is very a minimum cost, a very cost-efficient cost. I would say, sorry, a very reduced cost compared to what is an XRD and XRF system. We have to give you an order of prices. This kind of device is around 50,000 euros. When we are talking about an XRD and XRF system, we are talking about 100,000 euros and much more, millions euros, I think. I'm not sure about the cost that Cecil have invested in this in the system, the POLAP system, but I'm sure it's a very high cost. So the idea is to have a complementary measurement and to have an estimation with that could be certainly with a higher frequency. So the question now and the most difficult part in the job, I would say, are two difficult parts. The first one is to make the choice of best location and to use the best sample. We have developed in Nijmegen a sampling system that has supposed more than 2 months of full-time engineering. And the problem is that it's very difficult to implement this system because it's a higher cost. I think that if I had to develop certainly this system, maybe would suppose to spend maybe I would say certainly 50,000 euros more on the budget, and I out of budget right now because we have to deal with aspects that are very complex in the spectrometry. We have to use some diamonds, windows. It's something that is very, that's suppose, I think, very, that could be improved. I think it's totally feasible. But I think that maybe right now the priority was to better establish a correlation between infrared measurements, XRD and XRF measurements. And I think that maybe if I have to change something, I would go first for a lab system and trying to make a sampling system that is much more complex to implement and suppose much more modification on the facilities for Cecil. But I think that the second challenge in this case is we need a lot of data to establish a good correlation. But I'm quite confident because this is something that is been studied in the bibliography from in state of the art for decades, and I think they could have some interesting results that could provide some information on the quality of the clinker. And then I think that this part, to my opinion, maybe we have underestimated the workload to be developed in this project. And I think that this is not, I think, a high level. I think it's a lower level of development. And that's why maybe we have decided to make this change because I think the idea is to get some results, and maybe it's more interesting for Cecile to get less results but good results and try to go for something that is too ambitious. And for the other system related in profilometry and in thermal camera, I think the technology is mature and is ready. I think we could have some very good results for size estimation and volume production for profilometry. The key point is to make a good calibration of a thermal camera and to protect them from against dust, because dust is very is our enemy for optical and vision engineers. So for us, it's very very problematic because it can destroy your system, and that's why I have pointed out many times to protect the system, and this is a huge part of the development also. And maybe what should be another key point, I think, is what is important is to have a lot of data set, a very good data set of images. Here we have tried to bypass the problem related to different limitation due to pandemic situation. It was a very big problem for us because we need a lot of data set, and we tried to go for a test bench in order to approach what could be the images more closest as a reality as possible. But right now we have to deal with elimination problems for improving the segmentation, for estimation the size, for example. And this issue would be solved only with the integration in plant and taking a lot of images. So, but the technology is mature. After we can decide to go for a thermal camera in the short wave infrared range or in the long wave infrared range. If you want to have better quality images for segmentation and size estimation, you have to go for short wave infrared range. If you want to have more precise information related to thermal information, you have to go for long wave infrared range. So, and I think the technology is mature, so it could be totally integrated. So, well, I don't know if my answer has clear you more of a situation and the benefits of the technology.
Yeah, for sure. Yeah, that it's clear that there are a lot of challenges for you for these developments that are very let's say artisanal or manual. So yeah, it's homemade. So let's say it's not and it means that you need a lot of work to do it, and you have include.
That's it. Yeah.
You have include air curtains, fans for avoid the effect of the dust, and well, you have made tests in your facilities before install them in Cecile. So yeah, it's clear, Joe. That's clear. So let's see now, after the integration, the last validation phase, let's say, with all the data that you are going to obtain. It works, but yeah, for sure.
Yeah.
Okay, so thanks a lot, Francisco, and well, thanks a lot to all the speakers. If there are no more questions, maybe we can finish here the workshop. So thanks a lot for your time. Here you have the contact details for all the speakers. If you have any doubt or any question, you can ask them directly. But also I encourage you to follow us in our social media and check our website, because while in the following weeks we have another dissemination event with the related with the aluminium and steel sector that you can follow, and also we will have our final event by the end of October, the 25th of October. So I suppose that in the following days we will provide more information to all the people, to all the audience, in order that they have the opportunity to join us physically in Brussels, or if not online, for knowing all the results that we have obtained in this very challenging project. So thanks a lot for your time, and we can finish here the workshops. See you.
Thank you, Diego.
Bye.
Thank
Thank
you.
you very much, Diego.
Have a nice day.
Bye.
Thank you. Have a nice day.
Thank you.